Thank you, everybody, for coming. Thank you, Ganeshan, for inviting me, and H2O for hosting this workshop. So this is a view from the East Bay. This is what I get to see half the year because, we get a nice foggy East Bay. I'm going to tell you a little bit about some of the research I do. So I'm a scientist at Lawrence Berkeley Lab. So already big computers are actually helping at least some aspects of the government work more efficiently. Okay. I use giant computers, but so far I do not use AI. That's because our problem is incredibly well formulated. It's just challenging to do. So of course we'd like to learn how to introduce AI into our problem. And really we're looking at what's known as exascale computing, which is the generation after the computers that are showing up now, which will be deployed in a few years. And so what I'm going to do today is try to motivate for you why we need giant computers, what kind of science we would like to do that really needs these big computers. So here's something that's sometimes called the trumpet picture of the universe. So at the very beginning here, we believe there's a big bang, followed by a rapid inflationary period called inflation. And then a few very interesting things happen in the first few minutes after the Big Bang. What you may have heard about is something known as the cosmic microwave background. So roughly 380,000 years ago, hydrogen formed, so the electrons got sucked on the protons, and that means light was liberated to just run around the universe free. And then here we are way at the end. And so what describes all this, the evolution of the universe is known as the standard model of particle physics plus gravity. And that's basically described all the physics we know about in the whole universe. And we've only been around in the last little sliver of time to think about it. Okay, so like I said, the standard model has a few interesting things to tell us. The first thing that was sort of interesting is if you look very, very far back in the universe, at roughly 3 microseconds, so 10 to the minus 5 seconds after the Big Bang, so this is when the universe is very hot and compressed, there's about 1 trillion degrees Kelvin, we have the formation of matter. The next interesting thing that happened roughly 3 seconds after the Big Bang. And this is when the universe had expanded and cooled off a little to roughly 1 billion degrees Kelvin. So if you remember, 1 Kelvin is equal to 1 centigrade in terms of the units. Like a difference in 1 Kelvin is like a difference in 1 centigrade, which is 9/5 of a Fahrenheit. So this is still pretty hot. And then, like I said, 380,000 years after the Big Bang, protons, so the plasma in the universe expanded and cooled to the point that electrons got captured onto protons to form hydrogen, which is electrically neutral, so the photons could then roam free through the universe. The photons became liberated. Okay, and then it took 200 million years in order to form the first stars, roughly. And so the universe had to expand for quite a ways and cool off to about 20 degrees Kelvin. And what this is, it just gives you a sense of how weak gravity is compared to everything else. So to us, gravity is the most important of the forces we know about, but that's because we sit on top of the Earth. There's this massive ball of stuff underneath us that holds us down, but it's incredibly weak compared to everything else. So it takes 200 million years for gravity to pull everything back in and actually form a star. And then for the rest of the universe, you have the creation of stars, the deaths of stars, the formation of nuclei, heavy nuclei, and everything else, and all the interesting stuff you can see when you look out in the universe. For example, you probably know about supernova explosions. When big stars get too old, they collapse under their own weight, and then they explode in these fantastic explosions. And in fact, that's where almost all the heavy elements come from. So all the fluoride in your toothpaste comes from supernova explosions, for example. Okay. Now, I'm going to tell you about the standard model of physics, but I want to emphasize for you another thing we know is that, in fact, everything we know about only makes up 5% of everything we think is out there. So we have a very limited ability to explain stuff. The stuff we can explain very well, but it only makes up like 5% of the stuff out there. Only 1% you can even see. That's the stars. And then there's another 4% of gas. So this is just dark stuff, and we can only tell it's there because light bounces off of this stuff as it travels from one star to us. And then something like 25% of the universe is made out of something we call dark matter. We call it dark to mean we have no idea what it is. All we know is it's gravitationally attractive. And then everything else that we call dark energy, and we know even less about that. Okay, what I'm going to do is I'm going to focus on one particular aspect of the evolution of the universe, which is the formation of light nuclei. So what are nuclei? You have a proton and a neutron. Those are nucleons, the basic objects that form a nucleus. Hydrogen has a single proton. There's another nucleus called deuterium, which is a proton and a neutron bind together. So if you've heard of heavy water, it's deuterium. Even heavier water is tritium, so you get two neutrons combined with a proton. And that's used in nuclear fusion reactors. So it happens to burn in the sun. Well, what I should say is it's used in attempts to build fusion reactors, which would be a source of clean energy. And then carbon has 12 nuclei, has 6 protons and 6 neutrons. So this is what I mean by nuclei. And what you'll see is how does the formation of light nuclei in the early universe happen? So this is a period known as Big Bang nucleosynthesis. It's when the universe was roughly 1 trillion degrees Kelvin, expanding and cooling off to about 1 billion degrees Kelvin. And again, this is from about a few microseconds after the Big Bang to a period of just a few minutes after the Big Bang. So, in case you didn't know, if you have a system, all systems want to relax to the lowest energy state possible. So if you're on top of a hill and you let go of your legs, you're going to fall down the hill because it's a lower energy state. So a neutron, you may not know, is very slightly heavier than a proton. So here I'm using it in units we think of, and I know this doesn't mean anything to you, but the difference between the weight of a neutron and a proton is 1.3 mega electron volts. What does that mean? I'm not going to try to explain it. I will tell you that half the mass of the neutron plus the proton, or roughly the mass of these two things together, is 938 mega electron volts. So what you can tell is a factor of 1,000 difference. So it's a very tiny splitting compared to the mass of these things. And to put that in some scale, what might mean something to you, hydrogen, if you wanted to knock an electron off of a proton so it was charged, you had a charged proton, that would cost you 13 electron volts. So nuclear physics happens at a scale 1 million times more energetic than atomic physics. So all chemical reactions like batteries, these happen at electron volt scales. Nuclear physics happens at 1 million times that. That's why nuclear bombs are so explosive. They have so much energy packed in them because the scale of nuclear physics is much, much higher than what we're used to. Okay, so a neutron is a little bit heavier than a proton, so it's going to decay into a proton. And that decay is roughly 15 minutes. So this is the lifetime of the neutron. So if you have a bunch of neutrons sitting around, statistically, they will decay to protons in about 15 minutes. So you might ask, if you didn't know, why are there any neutrons in the early universe at all? Why didn't all the neutrons decay to protons? Well, it turns out nuclear physics is what happens. So here I start off with a system of 2 neutrons. I can decay to a neutron and a proton. And the reason you don't just go to a state of 2 protons is there's the first nucleus, deuterium, which I mentioned earlier, has a lower energy state than 2 protons. And so if a neutron gets captured by a proton, it becomes bound and it is no longer able to decay because it's energetically disallowed to decay up to 2 protons. So there's something known as the deuterium bottleneck. I won't try to explain why. The deuteron is not bound by very much energy. The one thing I'll tell you is a typical nucleus has 8 mega electron volts of binding energy per nucleon, whereas deuteron only has 2.2 total, or 1 per nucleon. That means it's easy to break it apart. And the early universe had roughly 1 billion photons for every proton or neutron. And so because of all these photons running around, they keep knocking deuterium apart until the universe expands and cools to a temperature of only about 100 kilo electron volts. So this is 10 times smaller or so than the binding energy deuterium. Once you break this bottleneck, you suddenly rapidly form heavier nuclei. So there's tritium, I mentioned before, it's a proton and 2 neutrons. And then there's this state helium-4 you may remember from chemistry. So helium-4 is one of the noble gases. Helium-4 has 2 protons and 2 neutrons. And if you remember anything from chemistry, you can take 2 electrons and you can put them in the ground state S wave, the ground state, because you can have a spin-up electron and a spin-down electron. So just the same, you can have a spin-up proton and a spin-down proton. And then you can also have a spin-up neutron and a spin-down neutron. They can sit very tight and on top of each other very compactly, and they have a lot of energy. So it's a very deeply bound nucleus. Okay. Turns out the early universe was roughly 75% hydrogen and 25% helium by mass. So if you weighed the universe a few minutes after the Big Bang, 75% would be hydrogen and 25% would be helium of all the stuff we know about. And this is actually very good because you may not know it, but the sun is a hydrogen star. It's almost all hydrogen. And that's good because it means it's a very stable star. It takes a long, long time for this sun to burn. The lifetime of a proton is roughly 15 billion years inside the sun. So the sun, if you didn't know, it takes protons and converts a proton into a neutron to form deuterium and eventually form helium, which is why the sun doesn't collapse. It's using nuclear fusion to heat itself up and keep itself from gravitationally collapsing. If we had less hydrogen in the universe and more helium, that would be bad for us because helium stars burn much faster. Because you have to get helium on top of each other, it becomes a much hotter system and it burns much faster. We wouldn't be here to think about it. So here's a little cartoon picture of everything I just said. I start off with a hot, compressed universe. I have some protons, a few neutrons, and the universe expands and cools off. And these neutrons are decaying the protons the whole time. And once you break this bottleneck, you can suddenly form deuterium. The neutron binds onto the proton, and it can no longer decay. And then rapidly, you'll form helium-4. And then after about 15 minutes, all the remaining neutrons will decay away to protons. So we actually can predict almost entirely what the lifetime of the neutron should be using the standard model. And it turns out it's this number. It's 5,000 seconds divided by 1 plus 3 times some number we call GA squared. So with the standard model of physics and a pen and paper, I can calculate every single number here except for this GA. And this GA, I need a gargantuan supercomputer to compute. And that's because nuclear physics is hard.
What is that equation called?
This is for the lifetime of the neutron. So that 15 minutes that it takes for a neutron to decay comes out of this formula. It took years and years and lots of people to come up with the formula, but at the end you can write it down quite simply. Okay, so again, this is what I'm going to tell you about a little bit later, this what's called GA. I'll just leave it at that, GA. So can we determine what it is? Yes, but we need a giant computer. Okay, why would you care? Okay, so if you look in the early universe and you ask how much helium there was, I told you it was about 25%, we can actually do a much better job, and we know it's roughly 24.7% helium-4. There's different ways to measure the lifetime of the neutron, so you can do lots of experiments and measure the lifetime of the neutron. One of them is called a bottle type experiment. So if you can imagine trapping neutrons in a bottle, it's not quite so simple, right? Because what's the wall of some object? Well, to us, it's just a wall, but to a neutron, it sees other neutrons. So you have to trap them magnetically, and you can watch them decay. Or there's other type of experiments called beam experiments where you shoot them through and watch them decay as they travel through. And it turns out when you measure the neutron lifetime, you get 2 different answers depending on which type of experiment you do. The bottle experiment is more precise than the beam experiment. And if you notice the light, so then this green band here, this is the predicted abundance of helium-4 as a function of the neutron lifetime. And you can actually see both of them don't quite agree with the observed abundance of helium-4. This tension is not very much. It's what we call like a 2 standard deviation tension, which means we don't really worry, we don't lose sleep about it. But the difference between these 2 different measurements is a 4 standard deviation, so 4 sigma. So if you remember any statistics, that's a 99% probability these cannot be right. Both of them cannot be right. They're in conflict with each other. And so what we'd like to ask is one of these experiments incorrect? Is there new physics hiding in here? So what we really want to do with all this is try to find some new physics. I said there's all this dark matter and dark energy. Maybe dark matter can explain why these two things are different. Meaning the neutron could potentially decay to some dark matter state that we cannot detect because it's dark matter. Okay. Now what do we do? So here's a little cartoon picture. I have a neutron. I don't expect you to know about quarks and gluons, but it turns out a neutron is made out of 3 quarks. A proton is made out of 3 quarks. These are these lines here, sort of a cartoon depiction of this quark. And then at some point, the neutron will decay because one of the quarks will have this transition and spit off an electron, what's known as electron antineutrino. So they're described by a theory what we call quantum chromodynamics. I just made it colorful because why not? This is the fundamental theory of nuclear physics. This is what we cannot solve with pen and paper and why we have to use gargantuan supercomputers. And we use it with a method we call Lattice QCD. So this little grid under here is supposed to be the lattice. It doesn't mean we live in a simulation. It just means we use a simulation to try to figure this stuff out. Okay. And then we can try to calculate this coupling GA. So this transition where I go from a neutron to a proton has a strength that's proportional to 1 plus GA, and that GA is what I want to know. Okay, I won't expect you guys to remember how to do integrals, but I wrote this equation down. This is the whole theory of nuclear physics right here. And what you probably do remember, though, is you at least remember what an integral is. And so what this equation is, this theory, is I have an integral of integrals. So immediately you can see this is going to be a very hard problem to solve because, first of all, this is a 4-dimensional integral, and then it turns out this is an infinite dimensional integral. So it's kind of hard to do. So what do? You put the universe on a grid. You chop it into a lattice, and the neat thing is, this thing you can show is real and positive, and it's bounded by 1. So what does that mean? You can use this as a probability to do a Markov chain Monte Carlo. So if you know a little bit about Monte Carlo, basically you randomly sample your integral space, and that is the heart of what we do. We do have this Markov chain. It's a chain, so that means there's correlations between these different sets of field configurations we have to worry about. And at the end of the day, you can show the answer you want is at some finite n, just simply given by the average of some O here is just meant to denote some operator, averaged over the different possible ways this U field can fluctuate in your universe. And then you have some stochastic uncertainty that improves with 1 over the square root of n. Okay, just to give you a sense of scale. Usually, the little lattice spacing, the smallest distance scale we introduce, is about 10 to the minus 16 meters big, which is about 1/10 the size of the proton. And then we make our universe about 6 times 10 to the minus 15 meters big total, which is only about 6 times the size of the proton. So this is really tiny. We are about a meter. This is 10 to the minus 15 meters. So we're simulating a very, very, very tiny slice of the universe. And this is the one place where maybe AI can help us. I said I don't know much about AI, but what I do know is there's probably smarter ways to do this Markov chain Monte Carlo. And so that's what we're trying to figure out, how to use AI in our research. Okay, ignore most of this. I just want to use this one arrow here to emphasize to you why this calculation is so hard. It turns out, so if you want to do a calculation and get the right answer, you have to remove this little discretization scale. And how do you do that? You have to simulate the universe with different sized discretization scales and extrapolate that to 0. And the problem is, as you try to make the distance scale smaller, it goes like 1 over a to the 6th power. So if you make a half as big, it costs 64 times more computing. So that's where the cost comes in. That's a tremendously terrible scaling, but that's the absolute best we can do. Okay. If you remember a little bit of linear algebra, this is the slide for you. Here I have a cartoon of a neutron and a proton transitioning a neutron to a proton. Each of these fuzzy lines is what we call a quark propagator. So again, protons and neutrons are made out of quarks. This is the object we need to calculate, solve. And the way we solve it is there's some known matrix. It's a large matrix. It's about 400 million size in each dimension. But it is also a sparse matrix. But it also has a bad condition number. And it's equal to a delta function. If you don't know what that means, it means if x equals y, so x and y here are my space-time dimensions. If you're at the same point, you get 1, else 0. If you know anything about linear algebra, you know you can solve this equation with a conjugate gradient method. And basically, this is why video game users have made our research better, because video game users and movie watchers drove GPUs. And GPUs are really, really good at linear algebra. And so these have vastly accelerated our research. It was what's called a disruptive technology. When GPUs came along, it wasn't Moore's law. It was a very disruptive technology, got orders of magnitude faster. So this is what I said my talk had leadership class computing in it. So the computer we did most of the work on is called Titan. It's a machine at Oak Ridge. It's a GPU-CPU hybrid. The GPUs in Titan are actually 6 generations older than the ones coming out now. So they're the K20s. They're the first generation after the gaming cards, the old K20s. And all this gobbledygook up here is just to show you that there's a whole bunch of different parameters we have to tune and wiggle to do the calculation. And in the end, there's something like 500,000 different calculations we had to perform. And this just to show you the scale of the cost, the calculation I'm about to show you took 184 million Titan hours, plus 60 million Titan hour equivalents at Lawrence Livermore Lab. We generated something like 2 petabytes of data that had to get processed down to only a few gigabytes. And if you had a computer, a laptop computer, that had a huge amount of RAM, you could have done the calculation, but it would have taken it about 800,000 years. So that's just the scale of the calculation we're doing. And I have to thank my funding agencies, like the Department of Energy is the big funder. Okay, what's this slide? This is just to show you we actually got a number. There's a team of people. The reason our code works as well as it does is because we have a collaborator at NVIDIA, and she writes really, really good code. So on Titan, our code, which is a double precision solver, was getting 25% of the peak performance of Titan. And they measure the peak performance in single precision. So our code was ludicrously good. And then all those different parameters, I was telling you, we have to do all this different stuff. Each one of these points represents a calculation. We have to extrapolate it to this point, and we get our final answer. And then if you say, how well can we do to study that question, the neutron lifetime? Well, the first thing I can show you is, unfortunately, our uncertainty is still a factor of 6 larger than the experimental uncertainty. And if you remember, if you want to reduce your uncertainty by a factor of 2, you need 4 times the amount of statistics. So to go 6, we need 36 times more statistics to compete with the experiment. And here's the slide I showed you before, the 2 different ways to measure the lifetime experimentally. And our calculation, okay, unfortunately, it's not better yet. But what we're excited about is it turns out, I won't explain it to you except to say that this calculation is statistics limited. There's not a systematic. So a systematic would be some additive shift you weren't aware of that you couldn't improve with increasing your statistics. If we just add more and more computing power, we will drop this number. And so we're really excited about the next generation of computers, these IBM, NVIDIA hybrids, the Power 9 with the Volta and GPUs in them. So these is leadership computing. There's Summit at Oak Ridge, Sierra at Livermore. They're being installed now, so we're already compiling our code on them, and we're testing them out. And we're getting more than a teraflop per GPU, so this is fantastic. We will eventually be able to compete with the experimental precision. And the reason I'm here is because we're hoping to figure out how we might use AI to make our research better. Okay, thank you.